Look up on a sunny day, and clouds seem entirely peaceful. They look like weightless wisps of cotton, floating effortlessly across the sky. But if you could somehow pull a medium-sized cumulus cloud out of the sky and place it on a giant scale, you would find out it weighs about 500,000 kilograms. That is 1,000,000 pounds of liquid water suspended right above your head. 10 miles above the surface, the laws of physics remain in effect. Gravity constantly pulls downward on all that mass, grabbing the microscopic water droplets that make up the cloud, exerting an inescapable downward force on every single one. So if a cloud weighs 1,000,000 pounds and gravity is working the way it should, why doesn't that massive payload instantly crash down onto our heads? Understanding why that 1,000,000-pound mass doesn't plummet requires a shift in scale, diving past the white exterior into the microscopic space between individual droplets. At this level, every single droplet forms around a microscopic seed, a speck of dust, salt from the ocean, or smoke known as a condensation nucleus. These droplets are only about 10 microns wide. You would need 1,000,000 of them to create just one raindrop. Because they are so small, they possess a massive amount of surface area relative to their weight. This matters because of terminal velocity. As an object falls, the air pushes back against it, eventually reaching a point where the air resistance cancels out the acceleration of gravity. For a tiny 10-micron droplet, that resistance is incredibly high. It hits its top speed almost immediately, slowing its descent to a near crawl. The cloud's total weight is effectively fractured into billions of tiny parachutes. Gravity is still pulling, but the microscopic scale of the water ensures that the descent is a slow drift rather than a sudden fall. Even a slow drift would eventually bring the cloud to the ground. To keep it aloft, there is a secondary force rising from the surface of the Earth. As the sun heats the ground, the air directly above it warms up and expands. This air becomes less dense than the atmosphere above it, causing it to rise rapidly. These rising columns, called updrafts, act like invisible elevators pushing toward the upper atmosphere. As long as this upward speed outpaces the slow terminal velocity of the droplets, the cloud remains suspended. The air literally pushes water up faster than gravity pulls down. The process even generates its own fuel. As water vapor condenses into liquid, it releases latent heat, warming the air inside the cloud and providing extra thermal buoyancy to keep the system rising. This turns the cloud into a thermodynamic engine. It isn't just floating. It's a calculated physical balance where solar energy provides the mechanical work necessary to hold up 1,000,000 pounds of water. This balance is governed by the conditions of the atmosphere, and when the air becomes too crowded with moisture, the engine begins to stall. Turbulent winds inside the cloud force droplets to collide and merge. This is called coalescence, tiny spheres joining together to form larger, heavier drops. Once a drop grows large enough, its terminal velocity finally exceeds the speed of the rising updraft. Gravity wins the tug-of-war, and the water falls back to Earth as rain. Pulling back from a single storm, we can see the sheer scale of this atmospheric architecture across the entire planet. At any given moment, these suspended water systems cover 67% of the Earth's surface. This global cover regulates the planet's temperature by reflecting solar radiation back into space during the day and trapping heat near the surface at night. These clouds are a direct result of solar energy and air resistance working in tandem. They are the visible gears of a system that shields the Earth, maintains our global climate, and keeps the water cycle in constant motion.